I think you know him better than I do.
So we are moving into the the other end. We more or less started at the sun, and we've been moving through the system as depending on the impacts from the sun, and finally we've gotten to something that is more human based or humanity based, and so we've invited David Brain from University of Colorado to tell us about planetary atmospheres and habitability. David has an interesting lecture planned, including several breakout questions for you to work on. So, David, over to you.
Okay, thanks a lot, Nick. And hello, everyone. Good morning, good afternoon, good evening, good middle of the night. How was that, Nick? Did that cover the bases? Okay. So I'm an associate professor in essentially the astronomy department here at the University of Colorado. It has an acronym and lots of words in it, but it's basically the astronomy department. And my research kind of falls in the cracks between three of the traditional scientific disciplines at NASA. So NASA has 4 science divisions. One of them is heliophysics, another is planetary science, another is astrophysics, and the 4th one is earth science. And my research has always fallen between heliophysics and planetary science. I do planetary magnetospheres, atmospheric escape from planets, and climate evolution at planets. And in the past 4 to 6 years, I also have started to fall in the cracks between those disciplines and astrophysics as I try to port some of the information and measurements that we have in our own solar system over to the field of exoplanets. Being in the cracks between disciplines used to be a hard place to be, I think. You had twice as many funding opportunities, twice as many places to send your funding proposals, but you were low on the priority list in every single one of those opportunities, every single one of those calls. That's kind of shifted and almost reversed in the past 5 or 6 years, where NASA seems very interested in interdisciplinary science, things that draw connections across boundaries. So I will pull in probably all 3 of these disciplines in our time together today. You're encouraged to be interactive. I already know the things I'm going to say, so it doesn't particularly benefit me to say them all. I want it to be a benefit to you. So if we go off the rails completely from what I planned, that's entirely okay with me. If you have questions, if you have comments, we'll go where your interests are. And you can do that by unmuting, you can do that in the chat, whatever makes you feel most comfortable. And I have the participant window up too, so if you raise hand, I should be able to see that. Okay, I have 6 different parts for the 2 lectures today, and we'll try and make this as fluid as possible. But let's start with some planetary science, some basic descriptions of atmospheres, climate, and what we mean when we say habitability. A lot of what I'll discuss today is relevant for the atmospheres of the terrestrial planets in the solar system, the rocky bodies that have atmospheres. So here, scaled to size are Mercury, Venus, Earth, the Moon, and Mars as well. However, when we're talking about atmospheres, climate, and habitability, Mercury and the Moon really don't have significant atmospheres. They have bound exospheres. So the atmospheres of Mercury and the Moon are not collisional. Collisions are rare. And there's not enough pressure there to really have a serious conversation about habitability in the present epoch for those bodies. We could also talk about the giant planets. So to scale, here is the smallest of the 4 giant planets, Uranus. And it's not that much bigger than Earth. People have in their mind's eye the giant planets being enormous. And that's because Jupiter, to scale, would look something like this. However, when we start talking about exoplanets, planets orbiting other stars, You'll hear the term super Earth, or have probably heard the term super Earth used. And sometimes super Earth and sub-Neptune are synonymous with each other. So a planet that's somewhere between 1 and 4 times the size of Earth is a perfectly reasonable sized planet to be detecting around other stars. And we're even detecting planets as small as Mars around other stars in the present epoch. So the question arises, what are the atmospheres of these planets like? What are the climates like? Could these planets be habitable at their surface? Radius, by radius. Yes, so Neptune is about 4 times the radius of Earth. So somewhere between Earth and Neptune, you'll hear the term super Earth or sub-Neptune used. And if you're really in the field of exoplanets, those two terms have distinct meanings from each other. It's a separate size class. I'm not as far into that community for that distinction to matter to me. So let's go back to Venus, Earth, and Mars. And sorry about the cough that you'll hear for the rest of today. I got vaccinated like many of you. I took my mask off like many of you, and like many people everywhere, I promptly got a cold. And so the cough has lingered for the last week. So here's some basic information about the climates of the terrestrial worlds. Venus, Earth, and Mars, often communicated to students as a Goldilocks situation. Venus is too hot, Mars is too cold, Earth is just right. And in planetary science, the Goldilocks problem is a real term that's used to refer to the study of why the atmospheres and climates of these 3 objects differ from each other. Greenhouse warming of the atmosphere plays a hugely important role in Earth's habitability. If Earth did not have greenhouse gases in its atmosphere, the average temperature on Earth would be 30 degrees cooler, or below the freezing point of water. We have enough greenhouse warming in the atmosphere to take the global average temperature above 273 Kelvin, thereby making Earth habitable at the surface. Mars greenhouse warming, by contrast, is only 4 or 5 degrees globally. And the Venus greenhouse warming is hundreds of degrees Kelvin, making it incredibly unpleasant at the surface of the planet. Another big difference between the planets is the size of their atmospheres. And sometimes we use size as a term to refer to atmospheric surface pressure. Foreshadowing and a reminder, pressure is force per area. So when you're standing on the surface of a planet, the surface pressure is a measure of the weight of the atmosphere above you pushing down on you as well. And so Earth's atmospheric surface pressure is 100 times that of Mars, approximately. And it's 100 times less than that of Venus, approximately. So 4 orders of magnitude range in surface pressures. A final, I could spend a long time on this slide. So the final thing that I'll point out, and a thing that's always very interesting to me, is the compositions of the atmospheres of Venus, Earth, and Mars. Venus and Mars have very similar atmospheric compositions, roughly 95% carbon dioxide. And the next most abundant gas is nitrogen. And the third most abundant gas is probably argon. It's definitely argon for Mars. For Venus, it's a rough tie between argon and sulfur dioxide because of the volcanic clouds on Venus. Interestingly, Earth should have the same composition as these 2 other planets. But because Earth has liquid surface water oceans, the carbon dioxide can be removed from the atmosphere. It gets incorporated into carbonate rocks, and 95% of Earth's atmosphere is currently sitting at the bottom of the ocean, bound up in carbonate rocks. If we didn't have liquid surface water, then we would be 95% CO2 and a few percent nitrogen. Argon is our 4th most abundant gas, but oxygen has far surpassed argon in our atmosphere, and that's a contribution from life itself, we believe. The respiration of life has pumped oxygen into the atmosphere. It took, this happened around 2.5 billion years ago or so that our Earth's atmosphere became oxygenated, we believe, and it hasn't looked back since. Okay, What do I mean when I say habitable? Well, first of all, when I talk about habitability, I'm referring to the surface of a planet. There are many amazing places in our solar system and other places as well in the galaxy that may be habitable someplace other than the surface of the planet. The icy moons in the outer solar system are great places to think about life having formed and developed. When we think about exoplanets and planets outside our own solar system, that's a tough challenge. That's going to be hard to get any measurements to constrain whether life could be there. A more modest thing to think about is whether life could exist at the surface of a planet, something that might be observable remotely. So when we're thinking about the surface of a planet, and I see the comment, and I'll respond to it in just a minute. I think the phase diagram of water is a great place to start. There are around 6.5 billion species of life that have been detected at Earth. All 6.5 billion of them require water in liquid form to survive. So a going-in assumption for life anywhere in the galaxy or the universe is that liquid water is required. That may not be a strict requirement. There could be some other liquid substance that satisfies the same functions as water. But for now, let's just assume water is required. Also, because hydrogen and oxygen are two of the 3 or 4, maybe 2 of the 5 most common elements in the universe as well. So water is probably a very common liquid. So when we think about habitability of planets, we often think about temperature, things being too cold for life, things being way too hot for life. But that's our Earth bias because we always exist at 100 kilopascal. We exist at 1 bar of atmospheric surface pressure. So we mostly experience a range in temperatures in our daily or yearly experience. But when we add other objects in the solar system, we see that parameter space is widely covered, even by just the 3 terrestrial planets with atmospheres. And Earth conditions nicely straddle this dividing line between solid water and liquid water for surface temperatures. And of course, we also have water vapor in our atmosphere. So this pink oval shouldn't be taken too strictly. Mars, however, has a smaller surface pressure, 2 orders of magnitude lower, and it's a colder planet, which puts Mars barely around the triple point for water. Even if you could warm Mars up and get the temperature to be appropriate for liquid, there's still not enough pressure in the atmosphere to make water want to be a liquid. It very often will just transition between ice and water vapor without ever passing through the liquid stage. So a challenge for habitability on planets is not only finding the right temperature, being in the habitable zone of the star, the distance from the star that makes it so that temperatures appropriate for liquids are possible, but you need enough atmosphere there to provide enough pressure for water to stay in the liquid phase and not immediately change to a vapor phase. Venus, poor Venus, it's got many challenges. And there are recurring discussions of life in the clouds of Venus that are very exciting. And that just illustrates a little bit how open we have to stay, how open we have to keep our minds when we're thinking about habitability, but also how challenging it is to bound the problem. Okay, so since the orbital position of Earth is between Venus and Mars, do they have similar evolution? Yes. So the Earth, Venus, and Mars Earth, Venus, and Mars all started with hydrogen and helium atmospheres like Jupiter and Saturn. And that hydrogen and helium was gravitationally attracted from the solar nebula as the sun was forming. But they were too small to hold on to those atmospheres like Jupiter and Saturn have. They've held on to their 98% hydrogen and helium for the entire age of the solar system. Venus, Earth, and Mars were too small, and so that hydrogen and helium was easily removed from the planet. It was easy to give it enough energy to escape. What we have today are called evolved secondary atmospheres. So the primary atmosphere of hydrogen and helium was lost. The secondary atmosphere was outgassed from the interior through volcanism. And CO2 is one of the main constituents of volcanic gases. So all 3 planets started with the same composition. The fact that they were different distances from the sun and had different sizes and maybe even different rotation rates as well have all contributed to a divergent evolution between those 3 planets. And especially the fact that Earth started at a place that was right for water to be liquid at the surface. That has provided a negative feedback mechanism in Earth's climate, so that if you push Earth and make it too warm, the Earth system tries to pull things back to a temperature that's appropriate for liquid water. And if you push Earth and you make it too cold, the negative feedback in Earth's geologic and atmospheric system pull the climate back. And so Earth has always had, almost always been able to have liquid water at its surface, while Venus and Mars didn't ever achieve that negative feedback, we think. All right. Sorry about the cough. I have cough drops upstairs that I did not bring downstairs with me. Okay, changing climate. Yeah, that's a gerund phrase, and it could mean many things. What I mean by this is, how can we change climate? So let's start with our first breakout room. I want you to brainstorm on what you could do to a planet to change its climate. Assume the planet already exists, but that you have evil superhero powers. And so you can make huge changes to the planet if you want. So come up with at least 4 fundamentally different answers. Saying we made the planet warmer and we made the planet colder, that's the same answer. You change the temperature of the planet. All right, so you have about 6 minutes. Ready, set, go. Good luck. With my last name, there has to be at least 1 evil superhero question in every lecture. So that's the rule. So Dr. Brain wants you to do something drastic to a planet.
Do you have a pinky? Is your TA your pinky?
No, but the grad students in my department put pinky on my office door sign. All right, welcome back, everyone. So I first want to go around and get your most basic answers, the easiest ones, and then I'll go around and ask for maybe your most exotic answer. So I don't know how we should do this. I prefer maybe Nick or Dana or Catherine call on the groups if possible.
I'm gonna pick. Let's pick Brian's group. Give us one.
First, the most basic, obvious one.
Brian, Devo, Mateo, and you.
One thing we noted was to strip away the magnetic field.
Right?
Either through injection of SCPs.
And what would that do to the climate?
If you induce greenhouse gases, I guess your temperature in your atmosphere could increase.
Sorry, was that a second one, the greenhouse gas thing?
Or it is a byproduct of the
Got it.
magnetic field stripping.
Okay.
And Brian, call on somebody who wasn't in your group.
Group or Jay.
We can change the distance to sun.
Sorry, say again. I was chewing on my cough drop.
We change the distance to sun.
Okay.
It will affect the flux absorbed by the Earth.
Okay. Good.
And Jay, call on somebody who wasn't in your group.
Ragu.
I think I heard my name. And our simplest one was also changing the distance to the sun. So should we do a more complex one?
Sure.
So more complex one was adding life to the planet or oceans to the planet.
All right, let's go with life. How would that change the climate?
It adds other constituents that the atmosphere may not have had, and that could affect the temperature.
And call on somebody, Raghu.
Megan.
You could shrink the radius of the planet, and that would change the gravitational force and acceleration, or gravitational acceleration on locally.
How would that influence the climate?
That's a great question. Would it bring your atmosphere closer?
Actually, decreasing the size would decrease gravity, which would make your atmosphere more extended.
Oh, okay.
Yep. Excuse me, and it could also make atmospheric escape more likely. Good. Who's next?
How about Neelam?
We were thinking about the rotational axis, the angle rotation. Okay. So it will change the period of seasons and all, and the temperature also, which is.
Okay, great. Thanks.
Thank you.
Call on somebody.
Okay. Vicky.
We discussed having ice cover,
Okay.
which would increase the albedo and reduce the temperature.
Great. Thank you. And I now can see the breakout groups, but go ahead, Vicky, and call on another.
Coal.
We going more directly to what the first point kind of touches on. We discussed just increasing the proportion of greenhouse gases in the atmosphere, or decreasing.
Okay.
Which would obviously increase or decrease the temperature respectively. Or yeah.
I just picked one of those two.
Sure.
Good.
And how about Florian?
Hey. So what we also discussed was having a huge impact of an object, an asteroid, or small minor planet.
Okay. So changing the impact flux to the planet?
Oh yeah, sure. I mean, we thought about a really big impact, but yeah.
Got it.
And it looks like we haven't gotten anybody from Group 5, Grant, Sine, and Xiaoyan.
Hi. So we thought about all these things. In addition, there was oceanic activity. So if because of certain plate tectonics, ocean starts to behave differently, then air currents will be dependent on that, and then the number of cells might change, and that will affect the stability of that planet's climate.
Okay, and so is the change in the ocean or in the plate tectonics? I missed at the very beginning.
Either, because both will affect the air currents.
Okay. I'm going to add them as different.
Okay.
But ultimately, Plate tectonics will have more far-reaching changes than just the atmospheric circulation. I'll do it here. Okay, so let's start to wrap this slide up. Does anybody have one that they think is the most exotic thing that they thought of, the most far out?
So I just want to add another that rotation of the planet.
Okay, great.
Rotational field.
I want to add one thing, like as you told, the surface pressure.
Good.
High volcanism.
Yep.
Or gravitational force.
What was that last one?
Gravitational force.
Okay, so like, is change planetary rotation, is that it, or is it different from that? Okay, any others?
Cloud seeding.
Okay.
I'm going to throw in one of my own. Change the orbital eccentricity.
Ooh.
Yeah.
And we talked about stellar brightness. So if stellar brightness changes, increases or decreases.
Aha. Yep.
But the last one doesn't count, right? It's not something that you could do to a planet.
I'll allow it. I'll allow it.
But you can vary the total solar irradiance on the planet without changing the star.
Yeah,
No, but you are essentially increasing the activity of the star.
But we're in evil.
The judge has allowed it already.
Yeah, we're in evil superhero mode, and evil superheroes don't follow the rules. So I will allow change the star. Okay, and I'll add one here just for fun. Let's add a large moon.
I was just thinking of that, David, and add a few more. I mean, what if we had many moons?
Aha, that's no moon. Okay. Good. Okay, great. That was fun. There are many blow up the planet or blow up the moon. All of the above. Okay, this is getting out of hand, mostly because of me, right? So, oh my, there's a lot of stuff on my screen. Oh, can't even see my slides. There we go. So all of these are acceptable, but the four most basic ones can all be represented in some really basic energy balance for planetary atmospheres. So often in planetary science or astronomy, you'll go through a really simple derivation of what the equilibrium temperature or effective temperature of a planet or any radiating object is. And that object that has a temperature and is radiates power per unit area at sigma t to the fourth. This is the Stefan-Boltzmann law. And that's the power per unit area. So you multiply back by the surface area of the planet. And this is how much total energy the planet is radiating away. Well, if the planet's not changing temperature, if it's in equilibrium, then the amount of energy that the planet absorbs must exactly equal this value, at least on a global average. And the amount that the planet absorbs can be represented by the solar constant, which for our solar system is, around 1360 watts per meter squared, as measured at the orbital distance of Earth of 1 AU. So one way to represent this is just scale everything to the energy input at Earth's orbital distance. Then you have to consider how much of that energy was actually absorbed by the planet. So you discount the amount that was reflected away, which was represented by the albedo. And all of this energy is being absorbed only on the day side of the planet, which is represented by a circular disk with radius radius of the planet. So in this energy balance, you'll notice that the radius of the planet to 0th order doesn't influence the surface temperature. However, there are indirect effects of the radius of the planet. It does influence the amount of internal heat in the planet and therefore the outgassing. And it does influence the vertical extent of the atmosphere and whether atmospheric escape is likely. But to 0th order, radius of the planet doesn't matter too much. Instead, what matters is the solar output, S, the planetary albedo, A, the greenhouse content, which I'll get to in a second, and the planetary orbital elements, not only the distance of the planet from the star, but the tilt of the planet and the orbital eccentricity as well, which aren't represented so simply in this really high level 0th order equation. The effective temperature of the planet, the temperature at which it radiates to space, isn't the same as the surface temperature of the planet if there are any greenhouse gases present. And that's because of how the greenhouse effect works. And so in a very simple model that relates the surface temperature to the temperature at which the planet radiates away, the relationship, the scaling factor that relates these two temperatures is the optical depth of the atmosphere, basically how much infrared absorbing gas is present. And so that optical depth is a way to think about the greenhouse gas content of the atmosphere. So to 0th order, these are the 4 main things that can happen to a planet to change its temperature and therefore change its climate. Of course, many of these other things as well can also more indirectly influence the climate too, adding a moon, blowing the planet up, having really large impacts. They can all be important. And all of these things can change with time, which makes thinking about atmospheric evolution either really fun or really hard. A couple of examples here. You probably have already heard about this or already in this summer school or already knew about this, but the total luminosity of the sun changes over time. The early sun was faint compared to today in terms of its total energy output, 25 to 30% fainter long ago. And the luminosity of the sun continues to increase over time over long sort of billion-year timescales. Another one that you may not have heard about so much is the tilt of Mars, because Mars does not have a large moon to stabilize the tilt of the planet gravitationally. The tilt of Mars can change wildly over relatively short amounts of time. Millions of years are represented between these two hash marks, 2 million years. And the obliquity of the planet, the tilt of the planet, wobbles back and forth by 10 or 15 degrees at a time. And this is based on theoretical calculations, but observations we have of the Martian surface, various geochemical observations, as well as geomorphology, suggest, and layering in the polar caps as well, suggest that this kind of model prediction is probably correct. The Mars tilt changes back and forth, and that can shrink and grow the polar caps on Mars incredibly. Okay, what's some evidence for climate change? Well, just a little bit of evidence for each of the big 3 terrestrial planets. Venus has relatively few impact craters, and we can use the number of impact craters on the surface to tell us how long ago the surface was molten and not able to accept any impacts that get permanently recorded. The number of craters on the surface of Venus suggests that the entire planet was resurfaced at some point in that past 500 million years. And there's debate about whether that happened all at once or a piece at a time over the last 500 million years. But this would have led to lots and lots of outgassing on the planet and a change in climate. Another piece of evidence that I'll talk about in a minute are isotope ratios. So for now, just retain the idea that isotope ratios can change in an atmosphere. Deuterium and hydrogen, the ratio of those 2 isotopes tell us that the atmosphere has probably changed. For Mars, also isotope ratios and elements in the atmosphere like argon can indirectly tell us that the atmosphere has changed, and I'm happy to answer questions about why. But also the fact that we see dried up riverbeds on the Martian surface where water flowed downhill in channels and carved the surface. And the fact that when we remotely sense the surface from space, we see phyllosilicates, I love silicate. These are clays on the Martian surface that form in the presence of standing liquid water. That is not possible. Neither of these two things are possible on the Martian surface today. The climate, the atmosphere must have changed over billions of years. And for Earth, there's abundant evidence both on short time scales and on really long time scales. And we have different scientific ways of accessing climate records on Earth. In the recent past, trees and coral are good ways to understand how climate has changed. Ice cores in Antarctica help us access sort of 100,000 year timescales. And then on million-year timescales, we have to rely a lot more on almost pure geology to understand how the climate has changed over time. So let's do isotope ratios and then maybe stop there for part one. And then I'll give you a question to ponder as you go into the break, and then we'll come back. So isotope ratios, question, break is what we'll do. So isotope ratios in atmosphere, why do they help us understand how atmospheres have changed? So here's a really old diagram from 1972, the year before I was born, of the abundance of different elements in Earth's atmosphere as a function of altitude. At lower altitudes, 100 kilometers and below, the change in density of every single element in the atmosphere is roughly the same. They all follow the same decrease in density with altitude. They're all in hydrostatic equilibrium together, and the atmosphere is well mixed. But when you get up high enough, collisions start to become a little more rare. And then we enter a regime called diffusive equilibrium, where diffusion becomes important and each species behaves independently of the others. They all have their own scale height, their own different decline in density with altitude. And the less massive species do not decline in density very rapidly, while the very massive species decline extremely rapidly with altitude. And that's because the scale height of an atmosphere is inversely proportional, or scale height of a species is inversely proportional to its mass. So at the top of an atmosphere, the atoms and molecules that you find there tend to be not very massive. The atmosphere is enriched in very light stuff and doesn't have a lot of the heavy stuff present. Isotopes like deuterium and hydrogen, or carbon-13, carbon-12, argon-38, argon-36, isotopes behave chemically identically. So you can use those as good indicators of what's happened. And if an atmosphere is really enriched in the heavy stuff, that means the light stuff has been stripped away from the top of the atmosphere. So we can use these isotope ratios, for example, the D to H ratio on Earth, Venus, and Mars, to infer how much the atmosphere has been lost to space over long periods of time. And in many cases, here's for Mars, as much as 90% of the atmosphere has been stripped away over the history of the planet. Venus has very large D to H ratios. There's been a lot of atmospheric escape, a lot of climate change has happened in that planet. And even on Earth, it's happened as well. Okay, so now I knew we were going to get behind here, so don't worry. I have a plan for part two. But what I want to do is give you a question to just think about for part two of the lecture. And this is a quantitative question, so just think about the approach during the break. Suppose Mars loses oxygen atoms at a rate of around 10 to the 26 oxygen atoms every second. How much would the atmospheric surface pressure in units of bars change in 4 billion years at this rate? So that's the question to think about. And when we come back, you can tell me a bit about what approach you'd take to think about this. I am ready.
Welcome back, everyone.
Thanks. So I'll ask you about this question in a few minutes. And also, I don't know if anybody was intrepid enough to actually try to compute it, but I'll ask if anybody got numbers for it. Otherwise, I'll kind of show you how to do it and tell you what the answer is in just a minute. So, help, break. Oh, we just had that. Okay. So, moving from, very general ways to change the climate of a planet, I want to focus for the rest of our time together on, or I want to be transitioning into the things that heliophysics most influences. And so as an introduction to that, here's a cartoon of various processes for adding or removing atmospheric particles from a planet. I used to have a really horrible PowerPoint diagram that I drew by inserting objects and arrows and stuff. And I was showing this really horrible PowerPoint diagram to a student, an undergraduate student who was double majoring in astronomy and graphic design at CU. And she emailed me 3 days after the lecture and said, here is a diagram that I made. And so now I always use the diagram that she supplied to me, which is really cool. So many of these processes will add atmosphere, outgassing, for example. Some of these processes only remove atmosphere, for example, chemistry driven by sunlight that leads to escape of particles. There are other processes like impacts that are a bit ambiguous, or chemistry as well, that can both increase atmospheric content or decrease atmospheric content. Very large impacts tend to remove lots of atmosphere. Smaller impacts tend to bring atmosphere and deliver it to a planet, for an example. Some of these processes here are sort of lumped together under a term atmospheric escape to space, which is a very generic, ambiguous term. But ion escape, sputtering, photochemical escape, and thermal escape. Those four processes together are often collectively referred to as atmospheric escape to space. Sometimes hydrodynamic loss is grouped in there as well. Okay, so atmospheric escape, let's talk about the theory of atmospheric escape briefly. A little bit of an aside about this diagram. This diagram started as a blue pen scribble on a piece of paper that I made way back in 2015 for a spacecraft mission called MAVEN that's currently orbiting Mars. And NASA wanted to make a graphic to use with the mission's first press conference. And so I scribbled something out about the sun spitting out the solar wind and a very large CME kind of engulfing the planet and atmosphere escaping. And the magicians at NASA, the magician graphic artists at NASA Goddard turned it into something incredibly beautiful, which always astounds me. And I often use as a way to highlight that there are many ways to be involved in space exploration and space science. And there's no person that carries all of the skill set needed to help us make progress. Okay, 3 requirements for a particle to escape from an atmosphere. It needs to have enough energy to escape. That means it needs to have kinetic energy that exceeds the gravitational potential energy of the planet. And so it needs to have a velocity that exceeds the escape velocity of the planet. Since different particles can have different mass, that means there are different escape energies for different species. And we often measure that escape energy in units of EV, electron volts. So Venus and Earth, you need about half of an EV for a proton to escape from the atmosphere. But at Mars, because it's a smaller planet, you only need 0.1 EV. It's not a very high threshold for escaping from the planet. Oxygen is 16 times more massive. You need a lot more energy to escape from the planet. Requirement number 2, that particle needs to be moving away from the planet. That seems silly, but in photochemical escape, when sunlight drives chemistry that leads to escape, there is usually a molecule, say O2+, a molecular ion, O2+. A photon is absorbed by that molecular ion and it creates O2, which then dissociates. And the dissociation products are given enough energy from that chemical reaction to escape from the planet. But there's no way that both of them can escape. because only one of them can break that bond and be moving in the right direction to escape from the planet. The other one, by definition, has to be moving towards the planet and can't escape. So this is also a requirement. Even though the second oxygen has escape energy, it's going the wrong way. Finally, no collisions. This is very good because that means even atoms and molecules down here at the surface of the planet where we live, if they have escape energy, they're not escaping either. There's too much stuff in the way. They're going to collide. So what that means is that escape proceeds from the top of an atmosphere, which seems like a very obvious point to make, but it's still a requirement. So some reservoirs for atmospheric escape to space. Here is a cartoon diagram of atmospheric escape, and I just got tired of putting red dots on the diagram to represent neutral particles. But a point that's often missed is that they're both neutral particles and charged particles at the tops of planetary atmospheres. The densities of both, when you get high enough, decrease with altitude. And the charged particles, the ionosphere, that's a layer that's not distinct from the neutral atmosphere. As a matter of fact, the ion densities in the ionosphere are usually orders of magnitude lower than the densities of neutrals at the exact same location. But because ions are charged, they are subject to additional physics that the neutral particles can't access. And so there's a really sort of rich set of physical processes to think about when thinking about an ionosphere. Other than that, the neutral particles that are escaping ultimately are in the exosphere, a region where collisions are very rare, but they originated in the thermosphere of the planet, just below the exosphere, a place where ultraviolet light and even X-rays from the sun are being absorbed in the upper atmosphere, and the temperature is increasing as you move up in altitude in the thermosphere, and that's energizing particles that ultimately might escape. Okay, and now a whirlwind tour of these escape processes, these four that get lumped together, and how it connects to heliophysics. First, of course, our star drives atmospheric escape, and that's many processes. And it's because of the energy outputs from our star, extreme ultraviolet light and X-rays, and also the stellar wind or the solar wind, which are particles, protons and electrons, of course. For a small planet like Mars, the upper part of the atmosphere becomes ionized through interactions with sunlight. So it has an ionosphere. Mars is small enough, its gravity is low enough that the atmosphere is incredibly extended. Anywhere you see green shading is the representation of the full extent of the Martian exosphere. And the exosphere of Mars actually extends probably 10 or 20 times the radius of the planet and can still be gravitationally bound for some of the particles at those locations. So one escape process is ion escape, something that I think about a lot. A charged particle, if it's sufficiently above the collisional part of the atmosphere, is subject to electric fields, both close to the planet and carried by the solar wind. Electric fields make charged particles accelerate, and there are different physical pathways for ions to escape from an unmagnetized planet like Mars. For a magnetized planet like Earth, all of the ions escape out of the cusp regions of the planet. Another process is called sputtering. Some of those ions that are formed in the exosphere of a planet, they are accelerated by electric fields and they will gyrate away from the planet, but sometimes the planet is in the way. So an ion that formed here tries to gyrate and escape from the planet, and it goes crashing back into the atmosphere. And it's picked up energy along the way, and it turns out it can splash out particles from the atmosphere collisionally. So this is called atmospheric sputtering, and the sputtering yield for some kinds of ions can be a factor of 100. A single incident ion can splash out 100 particles. This is all theoretical right now. We have yet to unambiguously identify this process happening in any planetary atmosphere, but our models suggest that it should be happening. Photochemical escape, I've mentioned a couple times. Sunlight breaks apart a molecular ion. One of those atoms escapes away to space. And finally, excuse me, thermal escape. This is the most fundamental escape process. This is sometimes called Jeans escape. It's been thought about since the 1800s. And this is because any distribution of particles has a variety of energies in that distribution. Even though you refer to the temperature of the distribution, the temperature is a statistical average. Some particles are going to be above average, some particles are going to be below average. It will typically follow a Maxwell-Boltzmann distribution or a kappa distribution of energies. And the particles that are above average might have enough energy to escape the planet. This is typically only important for really light species like hydrogen. And it's only important for hydrogen on Mars today, and to some extent on Earth, but not Venus. And I'll discuss why in a minute. But you don't see thermal escape of oxygen or CO2 from atmospheres. Those atoms and molecules are too heavy for thermal escape to be significant. Finally, all these processes together can interact with each other, and it makes thinking about it, I guess, deliciously complicated. And then when you throw in space weather on top of this and you amp up these energy inputs from the star for short periods of time and then have them back off, there's a lot to think about and a lot to factor in. So what's the dominant atmospheric escape process for Mars? It depends upon the species that we're talking about. I'll show this on the next slide, but I'll say the answer now. For hydrogen, the dominant escape process is thermal escape. For oxygen today, the dominant escape process is photochemical escape by a factor of about 5 over ion escape. So they're pretty close to each other. And it may be that long ago on Mars, ion escape or even sputtering was the dominant escape process for oxygen. For Earth, the dominant escape process is ion outflow for oxygen. And for hydrogen, it's a combination of ion outflow and thermal escape. Okay, so here's a summary of the escape processes I just talked about. And it's going to be here in the slides for you to, I guess, absorb later if you're interested. But I defined each of these processes as I went through the slides. And with the exception of sputtering, we think we're able to observe all of these processes happening at least someplace in the solar system. And a lot of my professional life currently resides in ion escape. But I've increasingly incorporated the other escape processes into my, my research as I progress through my career. Okay, so let's go back to this question here for a minute. There we go. And I know that you haven't had time to compute it or anything like that, but I want to hear from you how you might approach a question like this. What would you try to do? And anybody can unmute and contribute. That would be fine.
Okay, I'll volunteer. So I think first, figuring out the total number of oxygen atoms lost over that time period, and then converting that to a mass. And then going from there, if you want to find a change in pressure in the atmosphere, since you mentioned at the beginning, pressure is force per area, we can find the gravitational force on that, I guess, like the total amount of oxygen that has been lost, and then multiply that by the gravitational acceleration given, and divide by the surface area of the planet, and that might give us a change in pressure.
Perfect. Everything you said is correct, and that was complete. So I would write that out in this way. The change in pressure is the change in force per unit area. The surface area of Mars is not changing, so that's the change in force per area. And force could be represented as, the change in force could be represented as the change in mass of the atmosphere times the gravitational acceleration per area. then the change in mass would basically be the escape rate, the escape flux, which is number per second. And then that number per second, you'd have to multiply by 4 billion years. And you'd also have to change the number to a mass. So you'd have to multiply by the mass of oxygen. Okay, and then times G over 4 pi radius of the planet squared. Okay, did anyone try to compute this and come up with an answer that they want to hazard a guess? Okay, and in bars.
I also got 0.1 like Florian bars.
Yeah, Florian and someone else got 0.1 bars.
Okay, great. Oops, that's wrong. So sometimes I lose my mouse. All right, there we go. Yeah, and here we have to, hold on. Doing annotate again usually fixes it. Good. Yeah, here we have to multiply by 1 bar over 10 to the 5th Pascal. .1 bars is what some folks got. That is correct. So when I do this, I get 120. Ooh, I lost my cursor, and that's really large. I get 120 millibars. So a couple things to put this in context. Number one, 10 to the 26 particles per second. That's an unfathomable number. It's a number that's hard to wrap your head around. Let me provide 2 ways to provide context for that number. First, a mole of particles is 6 times 10 to the 23 particles. So this is, you know, between 100 and 1,000 moles of oxygen. Also, the surface area of Mars is on the order of 10 to the 18, 10 to the 17, 10 to the 18 square meters. So if you're thinking about, square centimeters, if you're thinking about how much escapes out of each square centimeter of the Martian atmosphere, that would be on the order of 10 to the 8 or 10 to the 9 for the escape flux from the atmosphere. Finally, 10 to the 26 is probably an order of magnitude too high for present day Mars for oxygen escape. We can account for 10 to the 25 easily. We might be able to account for 5 times 10 to the 25. So maybe it's a factor of 2, too high. So I rounded up for this number, 120 millibars. So that's 0.1 bars. Earth's atmosphere is 1 bar of thickness. So this is 1/10 of an Earth atmosphere on the top side that might have been lost. That's, you know, this is kind of an upper limit. If this escape rate has been the escape rate for the last 4 billion years. So that doesn't seem like enough to change the climate of a planet. On the other hand, the current atmospheric pressure at Mars is 6 or 7 millibars. This is a huge amount of loss. That would have made a big difference on Mars. Okay, so these are lots of different ways to think about this number. And I'll try and come back and put it in more context in just a minute, if I can find my cursor. So usually I have to draw and then clear, and then go away. There we go. Okay, so, oh, nice. Yeah, 10 to the 26 is a big number. Atmospheric escape, what do we observe? That was the theory. So at Mars, what do we observe? We observe all 4 of the main escape processes. Well, we observe 3 of the 4 main escape processes operating at Mars. Sputtering, we also think happens. So with our ultraviolet instrument on board the MAVEN spacecraft, we can see hydrogen very far from the planet. And using the brightness of hydrogen as a function of distance from the planet, we can get the scale height of hydrogen in the atmosphere. How quickly does hydrogen decrease? From there, we can get the temperature of hydrogen, and also from the absolute brightness, we can get the density of hydrogen. If we have the density and temperature of hydrogen in the atmosphere, we can then compute the escape flux from hydrogen. So all from an ultraviolet image, and we currently don't have images like this for any other planet in the solar system. As a matter of fact, I'll kind of jump to the end and say our observations of atmospheric escape at Mars are better than for any other planet in the solar system at present. So the thermal escape of hydrogen from an image like this is on the order of 10 to the 26 hydrogen atoms per second. Photochemical escape we can also infer through a combination of measurements and models. We need to know how much sunlight is entering the atmosphere. We measure that. We need to know the structure and composition of the atmosphere near the top. We measure that. And then we need to know cross sections for interaction, which we get from lab and modeling work. And we stir all this together in kind of a forward model that tells us how much oxygen should be escaping from the planet. And from photochemical escape, 1 to 5 times 10 to the 25. Ion escape, this is work from my research group. We can measure oxygen, molecular oxygen, and CO2 escaping from the planet. And the solar wind sweeps past the planet, and the electric fields near the planet and in the solar wind can accelerate ions away from the planet through different channels. When we add all that up, we get almost 10 to the 25 per second, but still less than photochemical escape today. Finally, currently we only have model predictions for sputtering. If we were to hold this lecture next summer, I may have observations to show you. We think on our spacecraft team, we're getting close to being able to prove that some of our argon measurements could only be caused by the sputtering process. So stay tuned there for a year. Regardless, this escape rate's super low compared to the other ones. It's not important today for things like oxygen. For argon, it's the only game in town. None of these other processes are effective at removing argon. For Venus, with spacecraft, we've directly measured ions escaping from the planet. This horrible diagram is a diagram where you're behind Venus looking towards the sun. Here's the outline of Venus and the warm rainbow colors. Don't get me started about the rainbow color bar, but don't ever use it. The warm rainbow colors tell you where there are lots of ions escaping from the planet. This was very early in a European mission to Venus, and I'll show you better data in a few slides that I didn't want to give away too early. So we only have measurements of ion escape. Thermal escape at Venus doesn't work. There's just not enough hydrogen escaping thermally for it to be important. Photochemical escape at Venus also doesn't work. The energy that we get out of those chemical reactions is absolutely defined by the chemical reaction itself, by the exothermic reaction. We know exactly how much energy the oxygen atoms acquire from that reaction. And that energy that they acquire is less than the escape energy of the planet. So photochemical escape doesn't work there. Sputtering escape, we have no measurements, so we don't know. Finally, Earth. Thermal escape surprisingly works at Earth, even though it's even a little bit bigger than Venus. The reason it works at Earth and not at Venus is because Venus has a lot of CO2 in its upper atmosphere, and CO2 provides cooling. And so it depresses the temperature of the atoms and molecules at the top of the atmosphere so that thermal escape isn't very effective. Earth doesn't have CO2 cooling at the top, and so that keeps the top of the atmosphere a little bit hotter than at Venus, and so hydrogen can effectively escape from Earth. So we have an estimate of the escape rate of hydrogen. Like Venus, photochemical escape doesn't work. Sputtering escape shouldn't work for Earth because the large magnetic field of Earth is going to keep ions from spiraling into the planet. The diagram I showed you before had ions being formed anywhere upstream of Mars or Venus, and some of them crashing back into the planet. an Earth's strong magnetic field, those ions are going to be guided by the magnetic field and redirected to the poles. There may be some sputtering happening at the poles. Certainly there are collisional processes there that cause aurora, but we don't think it's a particularly effective global escape mechanism. Ion escape has been measured, or at least ion outflow. So let me take a moment to distinguish between these terms. Earth is a big place, and Earth plus its magnetic field is an even bigger place. And spacecraft are really small. And so spacecraft have flown through Earth's cusp region and auroral oval and polar cap, and they've measured oxygen ions moving up away from the planet in those locations. And they get fluxes of those ions that are moving upward. They've clearly been accelerated away from the atmosphere. And that rate is somewhere 10 to the 25, 10 to the 26 per second. What's less certain is what fraction of those ions actually make it all the way out of Earth's magnetosphere and magnetic field and escape away to space. And some people that I ask say the answer is 50%, plus or minus 50%, because nobody really knows right now. Other people claim they absolutely know the answer. And everyone who I've encountered who claims that they absolutely know the answer has a different answer from everyone else I've ever encountered. So I currently view this as an unsolved question: how much oxygen actually escapes from Earth? So the escape might be unknown, but could be as high as this number. And if we take 50% of that number to an order of magnitude, it's still the same number, right? So this seems like a fair guess. Okay, so that's a review of the escape processes as they're happening at the 3 planets. I'm just going to quickly go through drivers because I want to get to something that's particularly interesting to me right now and that the community has shown a lot of interest in recently as well. Okay, so drivers of escape. And I was going to ask you a question here, but I want to really get to magnetic field influence, so I removed the question. So there are external drivers that could make escape rates change, even on Earth or Mars today. So changes in the total solar luminosity, the bolometric luminosity of the planet, are going to warm or cool the bulk atmosphere. That can have direct influence on the upper atmosphere and indirect influence on the upper atmosphere through things like chemistry. Or on Mars even, it can make dust storms more or less common. Dust storms on Mars occur during the summer months in the southern hemisphere because Mars has a very elliptic orbit. So the southern hemisphere is warmer. The southern summer is warmer than the northern summer. Dust storms on Mars are common during southern summer from all the warming in the atmosphere that tends to contribute to atmospheric motions and lofting of dust. Why does that influence escape? It turns out water hitches a ride on dust particles. And water has a really hard time getting high in the atmosphere because as it tries to move up in the atmosphere on its own, the atmosphere gets colder and colder and colder, and it can't make it through that cold trap. And it tends to sink back down, and its diffusion timescale through the cold trap is typically on the order of a century to get water from the bottom to the top of the atmosphere. Dust storms happen every Martian year, so every 2 Earth years, and water can hitch a ride on dust and be carried straight through the cold trap. And then it's in the upper atmosphere and it can dissociate, and hydrogen and oxygen can both escape. So the solar luminosity can contribute to changing escape. The solar wind can contribute to changing escape, and the solar wind, the mass loss rate of a star, should change with time. They're much better models than the one that I'm showing. There's a more recent model within the past 5 or 6 years by Tu et al. That shows that stars spin down as they age, but they could be fast rotators, medium rotators, or slow rotators. But that solar wind, the charged particles streaming from the sun, can be manifested. You could think of it as a dynamic pressure pushing on a system. You could also think of it as a momentum flux encountering a planet. and that energy and momentum can be transferred to an atmosphere. Solar EUV and X-rays. Even though the solar luminosity is getting larger with time, the solar EUV and X-ray flux is coming from the solar corona, from the solar atmosphere. And that flux is decreasing over time. So early in solar system history, the wavelengths of light that the sun was emitting that are important for upper atmospheres were much more intense than today. And that's been declining over time. And there, of course, there's short timescale variations as well. Finally, the interplanetary magnetic field is another external driver. Magnetic fields do no work. There's no energy present here, but the changing orientation of the magnetic field can change escape channels. Changing the strength of the magnetic field can influence how the solar wind interacts with the planet. So the interplanetary magnetic field can have indirect effects on especially charged particle escape from a planet. And this is an incredibly old sort of first principles back of the envelope model on how solar wind field strength would decline over time as well. So we've observed these drivers influencing escape rates at Venus, Earth, and Mars, all three. And I'll ask you to just take me at my word on that. But sometime I can show you lots and lots of slides on how, as the solar wind blows harder or weaker, the escape from Venus increases or decreases. And as the solar EUV flux increases and decreases over a solar cycle, the atmospheric escape from Mars increases and decreases. Even as the pointing flux, E cross B in the solar wind, as that varies, atmospheric escape from Earth, the ion outflow from Earth increases and decreases almost proportionally. Even seasonal changes on Mars, because of the dust that I just talked about, we see seasonal changes in hydrogen escape. All of these drivers we've observed influencing atmospheric escape from planets. So this goes to this sort of cartoon diagram. In the present day, with the exception of the solar luminosity, all of the other drivers we think should have been more robust, stronger earlier in solar system history. So the solar EUV flux, the solar wind, both should have been stronger. And also the extreme events, CMEs, flares, SEP events, should have been more intense and more frequent early in solar system history. So the back of the envelope question that I asked you to think about before, the Mars escape rate of 10 to the 26 oxygens per second, that's taking the escape rate that we observe today, maybe rounding up a little, and pretending that that escape rate has held for all time. In fact, that probably gives us a lower limit on the amount of atmosphere that was removed over time. It's basically taking the integral under this curve right here when I ask you to do that calculation. What's required is understanding all of the physics, understanding how each one of the knobs, solar wind, EUV flux, IMF, understanding how each of those knobs influences escape and how each of those knobs has varied over time, and then trying to make a better estimate of how much atmosphere has been lost from a planet. So for Mars, we've done this, and we can do it better, and we will continue to do it better. But our first sort of guesstimate at trying to properly do this tells us that somewhere between 0.5 bar and 1.5 bars of atmosphere have been lost to space over the history of the planet. This is enough to make big changes in the climate of a small planet like Mars. Okay, and then we can use the isotopes to calibrate what we've done. Okay, this is the last part, and I wanted to make sure we had 15 minutes for this part, and we have 16, so I'm very happy, even though that part went fast, sorry. So, so it was mentioned, very first thing for changing a climate is change the magnetic field of the planet. And I'm really happy to hear that answer, because I would say 15 years ago, it was just assumed in the planetary community, in the heliophysics community, and in the astrophysics community, that magnetic fields were good for life. That if you had a magnetic field like Earth does, then the atmosphere is more likely to be retained on this planet. That magnetic fields prevent stripping by the solar wind of the atmosphere. Nobody had ever really tested this hypothesis. It was just assumed. In the past 10 years, thanks to people in the community like Bob Strangeway, for example, Tom Moore at Goddard, Carl Schreiber, who used to be a dean of this school a little bit as well, people are starting to question this idea. So I want to ask a poll here right now in the chat. What do you think the answer to the question is? Don't type it yet. Think about your answer. Type it in the chat, but don't press enter. So A, B, C, or D. And on the count of 3, press enter. 1, 2, 3.
Ooh. All right.
Nice. Okay. Do we see everything but A, maybe? Yep. Wonderful. Great. We don't know the answer to this question right now, but I'm really excited to be thinking about the answer to this question and collaborating with people and the community to try to get an answer. And as a matter of fact, we just had a workshop, an international workshop for 3 days last week. And there are 155 people on the mailing list for the workshop. And there were 103 people in the Zoom meeting. And so there are lots of people who are interested in finding the answer. And everybody has a different skill set that they can bring to the answer. So let me talk for a few slides about why this is a question and where we're headed. So the old idea, and that maybe still the correct idea, is that magnetic fields should protect atmospheres, and it's really simple physics. So a magnetized planet deflects solar wind charged particles far away from the atmosphere. Since the solar wind doesn't encounter the atmosphere, then that's less energy for the top of the atmosphere, and the atmosphere can't escape as efficiently. Not only that, particles can get, especially charged particles, can get caught up and snagged in the magnetic field and never escape when they would have otherwise. Unmagnetized Mars, unmagnetized Venus, which you heard both of those things from Sabine Stanley yesterday or the day before, something like that. They're directly exposed to the solar wind. The solar wind intimately interacts with the upper atmospheres of those planets. So maybe those atmospheres are in greater jeopardy. And however, the rates that I just showed you suggest that it may not be so simple, because the escape rate of charged particles from all 3 of these planets, Earth, Venus, and Mars, based on spacecraft observations, is on the order of 10 to the 25th per second, 10 to the 25 particles per second from all 3. Give or take, we might be off by an order of magnitude or a factor of 4 or something like that in the rates. But certainly if Earth's magnetic field was so important, you would expect the escape rate from Earth to be down by a couple orders of magnitude or something like that. And it's not. It's comparable, at least the outflow rate from Earth is comparable to the outflow rate from Venus and Mars. So this is what made people like Bob Strangeway start saying, hey, wait, nobody's ever tested that idea. So here's the idea for why magnetic fields should not protect atmospheres. It's also simple physics, unfortunately. We have simple physics arguing for both sides of the question. So a magnetized planet captures more energy from the solar wind, a little bit like the sails on a ship do. We don't need the solar wind particles to directly impact the planet. We just need the energy from the solar wind, the momentum flux from the solar wind. A magnetic field gives a larger cross-sectional area to interact with the solar wind. the energy can be transferred along the magnetic field. And we know that this happens because Earth has aurora. We know energy is being transferred. And so in this case, the escape is not global from the entire planet. It's local in the auroral regions or in the polar cap of the planet, but it could be highly efficient there. We're getting just as much escape from this small little region on Earth as we do from all of Mars or all of Venus. So this is the argument in the other direction. However, there should be an asterisk on that statement that the escape rates from Venus, Earth, and Mars are the same. Not all escape measurements are created equal. They were done with different spacecraft at different times with different instruments, and those instruments had different energy ranges and different sensitivities, first of all. Second of all, you've seen, I think, Enlil model results before. This is an MHD model for the solar wind in our solar system. Earth is over here, Venus is here, Mars is here. Venus is closer, of course, than Earth or Mars. It experiences a different intensity solar wind on average than Earth or Mars does. They're often at different longitudes, so subject also to the different variabilities happening. And here's an example of a CME that happened in September 2017 that kind of directly encountered Earth, but didn't encounter Mars. And then another CME that came after sort of had a glancing blow on Mars. So the fact that the planets are at different places in our heliosphere means that it doesn't necessarily, it's not necessarily true that we can directly compare those escape rates from the three planets. If we were to put them, all three planets, in the same place, subject to the same conditions, then would the escape rates be the same or would they differ? This is a different way of expressing that. We can look at 2D histograms of the kinds of external drivers that Mars is subject to, the typical solar wind velocity and the typical solar wind density. And the solar wind density that Mars experiences can be pretty low. And then if we look at those same histograms for Earth or Venus, we start to see, and this is just for 2 of the 4 or 5 drivers, we start to see that the 3 planets experience different conditions. So the community is starting to go back and re-examine all of the measured escape rates and try and correct them and adjust them so that they can be more directly compared with each other. When we do that, we start to get results like this. And I'll point out that this is just from 4 published studies for these 3 planets, and they're on the order of 150 published studies. So there's a lot of work still to do. But when we look at the escape rate from Mars as a function of the solar wind pressure, it's kind of a complex scenario. And I've used these, shaded blobs to guide your eye. There are lots of individual lines here for whether we're at solar minimum or solar maximum. But the shaded blob gives you a rough idea. And the response of Mars to solar wind pressure is maybe comparable to the response of Venus to the solar wind pressure, but Venus doesn't experience low pressures. And then Earth has a really strong response to the solar wind pressure, at least in this one study right here. And so it suggests that the magnetized planet actually is more responsive to the solar wind than the unmagnetized planets, and that escape is more effective on a magnetized planet than on unmagnetized planets. That the magnetic field actually hurts more than it helps if you want to retain your atmosphere. Models can do the same thing. And so the community is starting to compare previously published model results, heavy ion escape rate, lots of different simulations of what that escape rate should be. And now they're being plotted as a function of solar wind pressure. It doesn't mean any one of these models is correct. They're all models. They all have assumptions, but the trends at least are suggestive that when you ramp up the solar wind pressure, an unmagnetized planet like Mars or Venus responds to that and escapes. The escape goes up. And we need to start putting Earth simulations on this plot as well, but that's a problematic thing to do because those simulations are substantially different. Another thing to point out here is that many models have run for the nominal solar wind pressure at Mars and changed other things instead. And there's a huge variation in how much escape comes out of these planets in the simulations. There's still a lot to understand. Just a couple more slides. One simulation, and there are now about 5 around the world that have approximately the same result. This is a former graduate student of mine. She took a simulation for how the solar wind interacts with a Mars-like planet and how much escape we would expect from a Mars-like planet. And it was not an MHD simulation, it had kinetic ions, so it was a hybrid simulation. And then she gave Mars a magnetic field. And she ran the simulation 7 times and changed the strength of the Martian magnetic field. And we expected as the magnetic field strength increased that the escape rate would kind of monotonically decrease or monotonically increase, that the magnetic field either enhanced escape or it reduced escape. And of course, the real answer is more complicated. For very low strengths of the magnetic field, escape was enhanced. For larger strengths of the magnetic field, escape then turned around and decreased again. So there's sort of a sweet spot in magnetic field strength that maximizes escape in the simulations. Now we have simulations from Japan and Europe and theoretical simulations from Europe as well that all reproduce this result. So I think this is my last slide, maybe there are 2. So the community is starting to get together to answer this question, and it's involving astrophysicists, people who study exoplanets, heliophysicists and planetary scientists, people who model Earth and magnetic planets, people who model unmagnetic planets like Venus and Mars, all having to talk to each other. And the plan is to construct a framework that allows anyone in the community to go to some sort of interface, maybe a web interface, and say what kind of star they have, what kind of planet they have, where the planet is located, what kind of magnetic field it has, and then spit out what the escape rates are. It's a really tall order, and it's going to involve, it's involving looking at published observations and observations we have from the planets in the solar system, and lots of simulations, and getting those together and getting them to agree with each other. So this is sort of where the community is heading. So I'll answer the question in the chat, and this is a question that I want to leave you with. I don't want to ask you to do it, but kind of ponder what you think the answer would be. So I'll stop there and let me look at the question in the chat.
I'll also point out that the schedule here is for us to basically transition to an office hour where you can just answer questions, discuss things with students at your leisure.
Got it. Thanks.
Dave, I really like the name of your old M-type star. Gives me ideas. Wonderful.
Thank you. Yeah, it's a very famous star. You might have heard of it before.
Yes.
I see. So could the escape rates, the comparable escape rates of Venus, Earth, and Mars be because Venus and Mars had already lost enough ions before? So to 0th order, yes, escape varies over time, and it's a whole system to think about. So Venus especially is difficult to think about because, well, Mars is a little easier to think about because escape is happening via all of these processes, but there's very little atmospheric source. So we really only have to think about the loss terms at Mars. At Venus and at Earth, we have to think about the loss terms and the source terms together. I often get asked if atmospheric escape is so important, or if magnetic fields are so important, then why does Venus have a 90-bar atmosphere? And I have two responses to that. One, atmospheric source processes have been active on Venus. It's a bigger baked potato than Mars is. There's been more outgassing, and so the source terms have contributed for a longer period of time. The other response is the isotope ratios at Venus tell us that atmospheric escape has been important. Maybe Venus lost 10 bars of atmosphere over the last 4 billion years. That would be 10 Earth atmospheres that it lost. And who cares? It still has 90 bars left. If it used to be 100 and is 90 today, that's probably not, a huge change in the Venus that we observe today. The second part is about temporal changes in Earth's magnetic field. They're both, of course, long-term changes, and you've had a lecture about dynamo theory here. And then there are the short-term changes in Earth's magnetic field, and by short, I mean on the timescales of magnetic reversals. And ever since I've been in grad school, people have been discussing whether Earth is about to enter a magnetic reversal period. And they base that wondering on how quickly Earth's magnetic poles are kind of wandering around in the Canadian Arctic for the South Magnetic Pole, for example. And I don't know whether it's about to enter a magnetic reversal period or not, but there's interesting science to be done thinking about how these heliophysical interactions with Earth's atmosphere would be different during the magnetic reversal period. Would the reorganization of Earth's magnetic field leave the atmosphere a little more exposed, a little more Venus-like or Mars-like in its interaction with the stellar wind? How would atmospheric chemistry change? Would homing pigeons ever be able to find their way from the start to finish of a race because they in part navigate using the magnetic field? There are all sorts of interesting things to think about there.
And in case you're wondering, we did put the question to Sabine, and she refused to commit.
Okay, great.
It either is or it isn't. She gave us good explanations for both sides, but
wonderful. I figured if anyone knows, she knows.
Exactly. Okay, well, thank you. That was great. As I said, we'll just transition over. If you want to take a brief breather or something, that would be fine. But I think on the schedule, the next 20 minutes are just going to be open forum. As long as anyone wants to ask questions, students want to ask questions or initiate a discussion, feel free. Unmute yourself. Okay, we have Regu has raised his hand. So, and yeah.
So thanks for a great talk, Dave. The question I had was the mental model based on physics that having the magnetic field funneling energy, so it's an efficient way of having these having atmospheric loss, that makes sense. But in the sense of observations based on Gunnell et al. That you were showing, right, for Venus, Mars, and Earth, one of the things that you pointed out is the difference from the sun, but the other difference is the atmospheric composition itself and the temperature of the exosphere there, right? So is that taken into account when looking at these observations?
Sorry, hold on. Not yet so much. I mean, it's acknowledged that there are many differences between Venus, Earth, and Mars, that atmospheric composition is one of the big ones, that exospheric temperature is one, that the chemistry that can happen in those atmospheres is also different. So at the level of trying to directly compare observations, this hasn't been taken into account so much. In simulations, I think people are getting a little closer. There are some groups that are taking, a Mars-like planet and putting an Earth-like atmosphere onto it, changing the composition to see how things change, or taking Mars and increasing its size to that of Earth and seeing how things change. So in simulation world, people are getting closer. Along these lines, I can't resist mentioning one particularly attractive approach for me. I think we're always going to have the problems that you mentioned of, observing differences between Venus, Earth, and Mars and wondering if it's truly because of the magnetic field or if it's something else.
Right.
And in simulation land, that's really great, but it can be difficult to validate those models. If you've invented some new planet that doesn't exist in the universe, how are you going to, you have to trust that the physics that you've extrapolated can truly be extrapolated. Right. That doesn't mean we shouldn't take both of these approaches. We still should. But a third one is Mars. Of course, I'm going to say Mars. The community kind of knows me as a Mars person. But Mars has these crustal magnetic fields that Sabine mentioned. And so there are regions of Mars that are magnetized and regions that are unmagnetized. On a planet at the same distance from the sun, at a consistent distance from the sun with a single atmospheric composition, a single size. So you have a built-in control experiment on one planet to test how atmospheric escape works from unmagnetized and magnetized regions and compare those, which I think is really attractive.
Yeah. Thank you.
Sure.
All right, Olude Hinwa, you have a question.
Yeah. Thank you, Prof. Dave, for your presentation. I actually want to ask, I saw where you showed in the slide that the increase in the ultraviolet light and the solar drives the loss rate. So I just want to ask, is there any, does intense geomagnetic storm could actually influence the loss rate? Is there any, are there articles with regards to looking at the loss rates when there's an occurrence of intense geomagnetic storm?
So are you asking for Earth or for
no, for Earth? Yeah, for Earth.
Yeah. So for let me see what I have here. So the question, hold on one second. The question was about changing ultraviolet fluxes, extreme ultraviolet fluxes onto a planet's atmosphere and how that changes the escape rates, specifically during extreme events like flares. So I don't have a perfect answer to that question, but I have a little bit of an answer. So let me show you two slides here. The first one here is for Earth, and this came from a scientist named Bob Strangeway in 2005. There's a spacecraft called FAST that flew repeatedly through Earth's auroral zones. It had a polar orbit, and it measured ion upflow. And during one solar storm, not a flare, unfortunately, but a CME. So during a CME, it made these measurements. So during a single CME, it measured ion upflow, and it also measured the pointing flux out in the solar wind. So how strong is the E cross B in the solar wind? And it showed that with some scatter, the solar wind has some control over what's happening to escape rates. So this isn't EUV flux, but it's instead solar wind control of escape. I'm not aware for Earth, it probably exists, but I'm not aware of the right papers for Earth that show how EUV flux influences it. But for Mars and Venus, we have that. So neither of these two figures is very inviting, but let's look at just oxygen escape for Venus at solar minimum and solar maximum. Right. And so you can see that there are maybe some deeper reds at solar minimum and blues start to appear at solar maximum. Blue means the oxygen, instead of leaving the planet, has turned around and is going back towards the planet. So during solar maximum, we get return flows at both Venus and Mars. This seems a little bit counterintuitive, that as you go to solar max, escape would go down. But remember, solar maximum can puff up the ionosphere. It creates so much ion production that it can be a little bit hard for ions to get out in the first place. This other one is for Mars, and it's from a really excellent scientist in my group. I know it looks confusing at first, but let's just look at green, the total oxygen loss from Mars. And the 4 data points are here in these green boxes, 1, 2, 3, and a 4th one over here. It's the escape rate from Mars as a function of the EUV flux that we've experienced. And the surprising thing is, or maybe the surprising thing is that this starts to saturate. We need more data, but it doesn't just keep increasing. At some point, there's an asymptote there. And we think, again, that's because all of the ion production in the atmosphere provides shielding currents. And those shielding currents make it hard for atoms to get out when the EUV flux gets too high. But this is an inference made based on 4 data points. Well, millions of data points, but 4 different time periods with 4 different EUV fluxes. So we need more observations to be sure of this answer. So I hope that helped. It wasn't Earth and EUV, but it was a little of both.
Great.
Thank you.
Sneha, you have a...
It's more of a philosophical question a little bit, that the way we are looking at habitable zones or habitable planets is based on our understanding of life on Earth. So if we really want to search how life on other planets would be, I'm not sure how to think about it, but we always go and search for water and oxygen and carbon dioxide and so on and so forth, which we know that life is based on. But I mean, how do you look at this question?
Yeah, I have some opinions there. They're not incredibly strong, but maybe some things to help contextualize. So, one of the phrases that people sometimes use is that we're looking under the lamppost, which, looking for the keys to your house that you lost.
Yeah.
The first place you want to look is under the lamppost, where their light has been shed there. So we know a bit about life on Earth. We know a bit about how that works. And because we understand that, that makes it easier to look for than something that we don't really understand or know about. How do we look for non-Earth life if we don't know what it is? That's one thing to think about. Another thing to think about is the requirements that we have for life on Earth. When you boil it down, they're really 3. One of those requirements is a source of energy. And that source of energy, even on Earth, varies. For most of us, the ultimate source of energy is the sun, but there's life that lives deep underground that never sees the sun and uses chemical reactions. So we think a source of energy should be available pretty much any place that we look, even Pluto. Number 2, we want the building blocks for life as we understand it. And currently those are 6 chemical elements, CHNOPS, carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. It's conceivable that there could be others. However, with carbon, hydrogen, and oxygen, we've already picked some of the most abundant elements that exist in the universe. So when we start adding things to the list, we're going to start adding things that are become harder and harder to find in terms of where we might look. It's conceivable that we should add things to the list, but it seems like with CHNOPS, we've probably already hit all the big ones that any life, any place might use. The third one is liquid water, which I talked about in the beginning. And all life on Earth uses it. Hydrogen and oxygen are abundant. But it's possible on Titan that in lakes of liquid ethane and methane, that life could exist there. Carl Sagan, I think, first proposed that. And then we have to think about what function, what purpose water serves. And there are a couple of aspects of water that are very appealing. First of all, a liquid medium in order to get those building blocks of life together. That's very important. And then water is also a polar molecule. So, you know, the H2O, the two H's are not straight out from the O, the molecule is bent, and that gives a net positive charge on one side, a net negative charge on the other side. It allows things to kind of orient themselves. And I'm not a biologist, but this has been called out as something that's particularly attractive in water's characteristics for helping organize the building blocks of life. So if we can find another polar molecule that readily exists as a liquid, I'm happy to go look for it. So I don't think that answered your question, but those are sort of my thoughts. It's a really hard question. Let's make things easy on ourselves to start. And B, when we start thinking about expanding the parameters, we need to think a lot about what really life on Earth needs and why it has those things.
All right, excellent. Neelam, you have a question too?
Yeah, I have a small question. Like, can we compare the atmospheric escape rate when during the conjunction event, the Earth and Mars aligned in line for the same CME, like for Earth and Venus, like that? So
yes, we can. This is a wonderful idea. And to some extent, it's been done once and not with a CME. So we had a spacecraft at Earth and a spacecraft at Mars, and we had a CIR pass both planets, a co-rotating interaction region or a stream interaction region. I think in the paper it was a CIR. And in that event, the authors found that the Martian escape rate increased by a factor of 10 to 100 during the time period of the CIR. The same CIR, when it encountered Earth, caused Earth's ion outflow rate to increase by a factor of 2 to 5. So the zeroth order inference is that Mars responded much more strongly to one of these CIR events. And it was a great effort by the authors. What I'm about to say is going to sound like a criticism of them, and it's not. It's a criticism of the available data. If you look at the Mars data 5 orbits later, after the CIR was clearly over, the escape rate at Mars again increased by a factor of 10 to 100. So maybe it was a coincidence that it increased right as the CIR was passing Mars. And also CIRs themselves, as you get from 1 AU out to 1.5 AU, that CIR might have evolved. We might have hit at a slightly different angle or something like that. So even having the same event strike 2 planets doesn't mean the 2 planets are going to experience exactly the same conditions. So there's maybe an asterisk next to that published result.
okay, thank you.
Thank you. In the chat, there's a request from Regu. He wanted to know more about this this community of scientists and maybe joining a mailing list.
Yeah, I'm happy to do that. And I want to be a little careful here. Because I want to be a little bit agnostic about this community. You know, the community last week was 155 scientists. So that's the community that I want to talk about. And there are people from the astrophysics community, people from planetary science, people from heliophysics. And basically, over the past 10 years, we've all started whispering and talking to each other. And now we're having AGU sessions on this topic every year. And in the European meetings, you can usually find one session that touches on this topic, or even the Japanese meetings. And so the reason I'm being a little careful is because I'm also in charge of a team science center, which is a smaller subsection of that community. It's about 15 to 20 of us. And So we currently have funding from NASA to examine this question and to come up with an approach to answering the question. But in a school like this, I don't want to spend too much time, talking about a project that I would like to see go forward. Instead, I'd like to talk about the much larger community. So I'm happy to add you to the mailing list for the much larger community, or keep your eyes open for upcoming meetings.
All right, great, thank you. And thank you again. I think we're done with the scheduled office hour time. So everyone, let's all thank Dave for a wonderful talk on a really interesting topic. And